All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good. Hopefully everyone's staying dry. It got a storm out of nowhere. Okay. All right. So plan for today. We're pretty much done with finite differences, and so we're moving on to finite volumes. So this is kind of exciting because finite volumes is, I would say, the predominant method that's used by most CFD codes out there, and that includes OpenFOAM. So knowing how finite volumes work and the theory behind it is good because then I think that means a better, stronger understanding of the tools that we're going to be using. It's exciting in that sense, but also a little disappointing in some sense too, because you're going to see that we spent all this time talking about finite differences, and we're going to do finite volumes, which is admittedly a pretty different methodology. But in some sense, we're going to end up in the exact same place that we did with finite differences. So, but how we get there is really important, and I hope to kind of make that pretty clear today, as well as over the next few weeks that how we actually get to that point is important. Okay. All right. So announcements. So homework 2 is out there. Homework 2 is a little bit more involved than homework 1, just because there's 2D stuff on there as well. But just make sure that you guys are working on that. I am working on the OpenFOAM stuff. So I've kind of had to try and I kind of failed and hit some dead ends a few times, but I think I do have a good plan going forward for that. So I'm hoping to get at least a couple OpenFOAM activities done before the spring break. That is my plan. But the first half of this class, unfortunately, is very theory heavy. But once we kind of hit the second half, then that's when we'll start to pick up on more of the OpenFOAM stuff. But I think it's a bit more clear. I was struggling a lot with the cluster bit, but I'm there's some changes happening behind the scenes that you guys will hopefully see and appreciate. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go and get started. Okay. So topic for today is we're basically going to be introducing the finite volume method. I mixed two words in my head. Method. There we go. Okay. So the kind of the acronym for finite volume method is FVM. So basically every computational tool has some acronym. You'll actually discover that computational people love their acronyms in general. There's an acronym for like almost everything. So, but the one for finite volume method is FVM. Okay. Okay. So let's kind of recap how we got here to this point in the class. So so far we've been covering what's called the finite difference method. Okay. And essentially, the way finite differences worked is that finite differences is a direct discretization of the derivatives in a differential equation. Okay. So in some sense, finite differences is very straightforward in the fact that you have your differential equation. We basically just we just basically see derivative, apply finite differences, right? And so, for instance, for just a general heat equation, right? So you have partial squared phi partial x squared plus partial squared phi partial y squared is equal to 0, right? So let's say that's our differential equation. If we were to apply finite differences, okay, we'd end up something like this, well, like what we were talking about last week. So you have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j all over delta x squared plus the y component, phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all over delta y squared. Okay. Right. It's literally just C derivative apply finite differences, right? And so kind of the thing that's implied in an equation like this, where when we see these phi values, so phi I comma j, I plus 1 comma j, right? These basically refer to the value of our solution at the grid points in our grid. Okay. Right? So sometimes we call them nodes, right? And so let's say that you have your finite difference grid here, right? So when you solve a finite difference equation, right, and you form your algebraic system of equations and you solve them for the solutions, right? Implicitly, what we're saying is, we're solving for the values of phi at wherever our grid lines cross, right? So when I talk about grid points or nodes, what I'm referring to are these points right here, right? And if you solve phi at every single one of these grid points, right, boundaries included, right? Right? You solve for the solution at every single one of those grid points, then you would be able to solve for the value of the solution throughout the entire domain. Okay. Okay. So finite differences, even though it's not strictly in the name, finite differences, we work off these grid points or the nodes. Okay. Okay. So like I've mentioned before, finite differences is always a good starting point, just because I think it's a very straightforward method to kind of understand. So you just take your derivatives and you apply finite differences, but it's not the only discretization scheme out there, right? So I think many of you may have also heard of the finite element method. Some of you may be taking EGME 410 this semester, or maybe you took it last semester. So finite elements is another methodology that's used to discretize these differential equations. Finite elements is great. It's I would say it's very widely used. In the space of structural design, I would say FEA is probably the most predominant. But in the world of CFD and heat transfer, we have another method called finite volumes, which is also the same thing. And so just at a first glance, finite volumes is another method that we can use to solve these differential equations. Right? It's another method for solving these differential equations computationally. The biggest difference with finite volumes is that, instead of focusing on the grid points in your mesh or your grid, we're instead going to be focusing on the cells or the elements per se. Okay. So if you look at our grid up there, right, we're no longer going to be focusing on the grid points. We're going to be focusing on essentially the spaces in between the grid points. Okay. So basically, something like this, right? So what I just highlighted in green there, that's what I would define as like a set or an element. Okay. I'm gonna try to use the term cell as much as I can in this in this class, just because not to kind of confuse you with finite elements. Although finite elements also similar methodology. You work on kind of the volumes that are created by these grid cells, right? But elements kind of has a different connotation. Finite elements kind of works a little bit differently than finite volumes. So I'm gonna try to use the word cell just because that's more accurate to finite volumes. Although growing up in the 90s watching Dragon Ball Z, I think when I say cell, I think of something else, another green thing. So, but that's what I mean by that. Okay. And working with cells kind of has a few strong advantages, specifically for thermal fluids applications. Okay. So already, if you take a classical fluid mechanics class or a classical heat transfer class, the concept of a control volume is something that's already kind of built into the theory of these subjects. Okay. So even though the math that we're going to be doing is obviously going to be different, but a lot of the same concepts and understandings of what you understand from control volumes and fluids and heat transfer, those apply here really easily. Okay. And because of that, we also gain a lot of really nice properties as well. In particular, when you're talking about fluids and thermal applications, this idea of conservation is really important. So conservation of mass, conservation of momentum. And it turns out that when you formulate your equations from a finite volume standpoint, you kind of satisfy these conservation laws just automatically. Because if you look at a particular volume, it's very easy to say that the amount of fluid coming into the volume has to be equal to the amount of fluid going out of the volume. That's one of the core tenets of conservation of mass. And that's something you kind of just get automatically. It's automatically baked into finite volumes. Whereas if you were to use finite differences to discretize Navier-Stokes, conservation of mass is not it. You can still definitely enforce it, but it's not as natural as in finite volumes. Okay? So that's kind of why in the CFD community, finite volumes has really been kind of the go-to method, just because a lot of things that a lot of features that we really value in terms of solution properties, finite volumes just kind of does that really automatically. Okay. Okay. So as we're kind of developing the theory for finite volumes, you might be asking yourself, why are we going through all this process? Because it's developing finite volume equations does take a bit more work than finite differences, but there is a payoff, okay, especially for all right. Any questions on this so far? Okay. All right. So let's talk about the concept of a self-centered finite volume. All right. So now that we're kind of shifting our focus to the cells in our grid, right? That kind of begs the question in terms of how are we going to solve our equations, right? So finite volumes and finite differences are similar in the sense that we are still going to be solving for discrete values for the solution, right? right? And so, eventually we're still going to obtain like an algebraic system of equations to solve for, a finite number of unknowns, right? But conceptually, we don't think of those unknowns being evaluated at the nodes. We instead envision them being at the centers of our sets. Hence the name self-centered finite volumes. Okay, so we have our grid. Okay, so say we have a grid that looks like this. Okay. All right, so we have 12 cells. So when we go through our finite volume kind of method and we obtain our system of equations, we're still going to obtain, solution our equations for phi1, phi2, phi3, phi4, phi5, phi6, right? So but now those values of phi, we're going to assume that they are located at the centers of our grid cells. Okay? And so all the same concepts about the grid still apply here. It's just that, there's that subtle shift in terms of where our solution values are located. Okay. So just like in finite differences, we still have a concept of the grid spacing, right? And so we have, let's say we have the grid spacing in the y direction, delta y. We have the grid spacing in the x direction, delta x. Okay. Right. So delta y, delta x are still there. But now that delta y, delta x, that tells us the size of our cells. So they're the same thing, right? And so they're basically the distance between grid points. It's just the way that we interpret them is a little bit different, right? Because the size of the cell is now something that's going to be an important property for us to work. Okay. One other subtle thing that you'll see as well is that because our solution values are at the cell centers, that kind of shifts their physical location as well, right? Because if you look at the x and y locations of phi1, for instance, right? Right, so phi1 is not located at the grid points, but we still think of the cell, we still think of the mesh in terms of the size of the cells. And so if you were to find the physical location for this, right? So the location for phi1 here, this would be delta x divided by 2. Okay. And then in the y direction, we have delta y divided by 2. Okay. So the physical locations are going to change a little bit. So if you're computing quantities that depend on x or y in your governing equation, just know that you kind of need to have that offset there. Okay. And the same goes for one-dimensional finite volumes as well. All right, so for one-dimensional grid, right? For 1D, it's a little bit confusing to kind of draw just because it's all within a line. But I'm using little circles to denote the grid points, and then the phi values are going to be, or the squares are going to be the locations of our finite volume cell centers. Okay. So, for instance, this is a cell right here. Let me use a different color. All right, so we say that this is a cell, this is a cell, this is a cell, and this is a cell. Okay. Right, so that's a concept of finite volume cell in 2D. Okay. And once again, usually when we talk about this, we're talking about, or when we're talking about the grid spacing, we're talking about the size of the cell delta X. So just know that the cell centers are offset just by a half. Okay. So the location for phi1 here, this would be delta X divided by 2. Okay. All right. And so kind of the implied nature of the self-centered finite volumes is that, once you compute the solution within that volume, it's assumed that the entire volume of that cell has the same solution value. Right? And so once again, you have this idea where, if you want greater solution resolution, greater solution accuracy, you need to make your cells smaller, right? Right? And how do we make our cells smaller? We increase the number of cells, we reduce the grid spacing, right? So a lot of the same concepts and kind of intuition that you gain from finite differences is still there. And so, none of that stuff kind of changes, but just the way that we get our equation at the end is going to be different. And the way that we kind of approach it is going to be. All right. Any questions on this so far? Okay, good. All right, so let's actually start talking about some of the mathematics of the finite volume method. So we'll get into most of it on Wednesday. When we actually take the diffusion equation and then discretizing to finite volumes. But let's talk about kind of the preliminaries to get. Okay. All right, so one really important theorem that we're going to be using a lot in finite volumes is the divergence theorem. So divergence theorem might be a concept that you learned in Calc 3 or multivariable calculus that you thought that you would never use ever. But here it is, and then it's actually very important for what we're going to do. Okay. Okay. So what is divergence theorem? So divergence theorem is one of the, I would say, pillars of integral calculus. Right. And the main thing that allows us to do, or the main thing that we're going to use it for, is that it allows us to transform integrals from one form to another form. In particular, the type of integral that it allows us to kind of transform between is a region integral, which I'll kind of define more deliberately in a second, to what's called a boundary integral. Okay. Right, and this is going to have quite a few advantageous properties for us, as we develop finite volume theory. Okay. So actually, I'm going to do this kind of reverse the way that I used to, because usually I kind of show you guys the 3D version of the divergence theorem and then kind of go down to 2D and then 1D. I'm going to show you the 1D version first, because the 1D version, you could argue is not really any math involved. That's just how integrals work. Okay, so there's a different version of divergence theorem in each of the dimensions. So let's look at 1D first. Okay, so our starting point for our 1D divergence theorem is the integral between a and b, of d phi dx dx. Okay. Now let's kind of dissect this integral a little bit to kind of see what we're looking at, right? So this is what I would define as a region integral. The reason being is that the integral or the bounds of the integration are defined across an entire region in that dimensional space. Okay. Okay. All right. And so if I were to draw kind of a one-dimensional domain, right? All right, and we'll say that the two endpoints of our integration are here. So we have x is equal to a on the left-hand side, x is equal to b on the right-hand side. Okay. Now, by performing this integral from a to b of d phi dx dx, right? What we're saying is that we're evaluating our integrand d phi dx at every single location between x is equal to a and x is equal to b. Okay. So our integration is taking place on basically we're basically evaluating the function at every single location within that set domain. Okay. So what is this evaluated as? Well, in this case, we don't actually need anything fancy. So this can just be evaluated just by looking at it, right? Because we have in our integrand here, we have a derivative with respect to x, and it turns out our integration variable is also x, right? And so if you were to evaluate this, right, the dx is essentially cancel out. And so we have integral from a to b of d phi. Right, and you have integral of d times something or d something, not multiplied. This is a differential operator. That's essentially a perfect differential of our variable phi, right? And so we evaluate this. Okay. You end up with just phi at b minus phi at a, right? So we basically perform the integral. The integral of d phi is just phi, and then we evaluate it at our two bounds, phi at b minus phi at a, okay? Now, if we look at this expression here, right, we have the difference of phi evaluated at two endpoints, right? We can make the argument that these are strictly just boundary terms. Okay. So no longer are we performing an integration at all points between A and B, right? In order to evaluate this, we just evaluate phi at x equal to A and phi at x is equal to B. Right? So in other words, we're only evaluating phi here and phi here. Right? At x equal to A and x is equal to. Okay, and so in some sense, it doesn't really matter what value C takes in between A and B, right? In order to evaluate that expression there, we only need C at the end. Right? So this is the idea of the divergence theorem, is that, if you have an integral that takes place over an entire region, and there are derivatives involved, that's the other kind of prerequisite, is that there has to be derivatives in our integrand, then we can kind of use some math to kind of reform that integral in another form that's more convenient for us. And usually, it's more convenient for us to evaluate things just at the boundary rather than the entire, region of the original integral. Okay. Okay, so that's the idea in one dimension. So in one dimension, we didn't really have to invoke any special theory to just evaluate the integral. But this same idea is going to kind of, generalize to two dimensions and three dimensions as well. Okay. All right. Any questions on this, on the 1D theory? Okay. All right. So let's look at the divergence theorem in 2D now. I think with 2D, it becomes kind of more clear why we need this, we need this theory. Okay, so in 2D, the divergence theorem has the following form. Okay, so in 2D, our region integral is given by a double integral over a region A. Okay. Right. And our integrand in this case is the divergence of some vector field U. Okay. All right, so this right here is a region integral. All right, and so actually let me just make it clear. Let me go ahead and draw our 2D region here. Okay. So, for a 2D region, you can have any 2D shaped region. I just chose a square just because it's convenient to draw, but this divergence theorem also applies to, any shaped region as well. Circles, ellipses, ovals. Ovals are just ellipses. I don't know, I can think of another shape. Triangles, octagons, right? So any 2D shape, but squares are just most convenient. Okay. So in order to evaluate that integral, a double integral means that you're basically valuing the integrand at every location within the area of that region. Okay. Okay. So according to the divergence theorem, we can basically take that take that double integral and convert it into another form. So the converted form is the following. Okay. All right. So instead of a double integral, we are now going to have a line integral. And this is going to be line integral of our original vector field U dot product with N, okay, ds. So this right here, this is a line integral. This is a line integral around the boundary of our two-dimensional region. Okay, so instead of integrating within the center of our 2D region here, right? We're essentially going to be evaluating an integral that goes around the outside like this. right? So in red here, I basically have a line integral around the boundary of our region. All right. So why would we do this? So why would we kind of go through the trouble of converting these integrals? Because honestly, neither of those integrals seem particularly nice to evaluate. Okay. So the reason we're doing this is because when you're talking about fluids, and you're talking about fluids within a fixed region of space. Think back to our review of fluids. I know it was several weeks ago, but think back to our discussion of the Reynolds transport theorem. Okay? So if you think back to Reynolds transport theorem, right? One of the kind of the core ideas of Reynolds transport theorem is that in order for any kind of quantity to be transported within the volume, it has to cross one of the region boundaries. Okay? So the thing with a lot of conserved quantities is that you can't just spontaneously create or destroy things out of thin air, right? So you can't just create mass out of thin air. If fluid mass is going to appear within a volume, it has to get there somehow, it has to cross a boundary, right? Same thing with momentum. Although with momentum, I know we can apply external forces, but for the most part, we say that in order for momentum to get there, it has to cross the boundary. Okay. Right. And so in a lot of sense, you can understand, a lot or basically everything about the fluid mechanics within a volume just by seeing what's occurring at the boundaries. So that idea that we're essentially looking at fluid flow situations, right? In finite volumes, you can think of finite volumes as a bunch of really small control volumes that are all just basically connected to each other, right? And so if you look at each control volume and you formulate your mathematics to what's happening around the boundaries, then it becomes a lot more easy to kind of see what's going on. Okay. The other benefit that we get from this, right? You may have picked up on this already, is that if you look at the two integrals here, right? And this even goes back to our 1D integral as well, right? If you look at our region integral, right? We essentially have a derivative term within our region integral. Right? So when you take the divergence of a vector field, essentially you're taking its derivative. Whereas if you look at our boundary integral, there's no derivative. Right, and that actually helped us out quite a bit. So, when we're kind of, evaluating our equations, right, the less derivatives that we have, actually the better it is for our solution. Okay. So, in here, you can see that, we go from derivative to no derivative, but the exact kind of definition of what divergence theorem does is that it actually lowers the order of the derivatives in the integrand by one. And this helps a lot with our derivations. So that's kind of the two main reasons why we do divergence theorem is, it kind of reformulates our equations in a way that makes sense given our physics, right? Um, and also, it just kind of helps with the mathematics. So we evaluate less derivatives, which is always good. Okay. Any questions on that? Okay. All right, so I'll give you the 3D one. We're not actually going to use it because we can't really do anything analytically with 3D just because it's just too cumbersome. But I did want to show you it. All right, so divergence theorem in 3D is the following. So a region integral in 3D, of course, would be a triple integral. You have a triple integral, and that's over a volume of the divergence of your vector field EV. Okay, so this is our region. Right? And this gets converted into a boundary integral. So now the boundary of a three-dimensional space is a surface, right? And so instead we have a surface integral over the bounding area, okay, which is an area there. All right, so we go from a triple integral on a volume to a surface integral on just the bounding area. Okay. Okay, but again, we won't really do anything with that. That's just kind of for your own trivia. Okay. Okay. All right, so that's divergence theorem. So that's the first kind of integral theorem that we can see. And if it's not obvious already, the main difference between using finite volumes and finite differences is that we're going to be doing a lot more integration. Okay? So the way finite volumes essentially works is that whatever governing equation that you have, right, whether you start from the general conservation equation or you're starting from Navier-Stokes, right? The main kind of step that you're going to do is that you're going to integrate your governing equations across the region of whatever your finite volume cell occupies. Okay. All right, and so if you have, a grid that looks like this, right? Essentially, you're going to be evaluating your integral, or you're going to be integrating the governing equations across each cell, right? Right. So in reality, you're applying those integrations across every single cell. Although there are shortcuts we can take because most of the time we're working with cells that are either equivalent to each other, or there's other shortcuts we can take even for an unstructured grid. Okay. And then by evaluating those integrals and then applying, some kind of useful integration rules like divergence theorem or trapezoidal rule, we'll go over that soon, right? By applying those integrals, we can then obtain an algebraic equation for the values of our solution at the cell centers. Okay. So the goal of finite volumes is the same, right? So, we're still seeking a set of algebraic equations that we're going to use to solve for our solution at these discrete points, right? That's just the nature of many computational methods, just because computers they're just really good at linear algebra. And so, if you can take your problem and turn it into an algebra problem, that's always a good thing. Okay. Okay. And the goal is to solve for the value of our solution at every single cell center within. Okay. Okay. All right. So let me give you kind of a preview of kind of what this looks like mathematically, but we'll go into more details about it on Wednesday. Okay. So if you're given your general conservation equation, Um, and I'm going to put it in a different form. So I'm going to put it in vector form. And so our general conservation equation looks like this. We have partial phi partial t plus divergence of the velocity multiplied by phi is equal to divergence of the gradient of phi plus q. Okay. So we probably haven't seen our equation in this form. So let me just kind of label all the terms here. So this partial phi partial t, this is our unsteady term, right? This divergence term here, this divergence of the velocity multiplied by our solution here, this is our convection term. Right, this guy here that involves the gradient of our solution, this here is our diffusion term. And of course, Q here is the same. This is our source term. Okay. So just for the sake of simplicity, so I wrote out the full equation here. But just for the sake of simplicity, just because we haven't gotten to it yet, we're going to assume the unsteady term is 0 for now. Okay. So we're going to assume steady state. And so all that we're left with is just the convection term, the diffusion term, and the source, right? So we've already dealt with all these terms of finite differences. But let's see how it works in finite volumes. Okay. So the first thing we're going to do is we're going to integrate this entire equation over the region of a theoretical finite volume cell. So basically every term there we're going to integrate, and we're going to integrate them separately, right? So remember, even though integration is a scary operation in some case, it is linear. And so when you integrate the entire equation, we can integrate each of the terms individually. Okay. Okay. And so let's assume that we're in 2D for now, just so that there's no ambiguity in terms of how many integrals we need. So that means we're going to apply a double integral on every single term here. So we have double integral of the divergence of the velocity multiplied by phi dA, okay, is equal to double integral over the area of the divergence of the gradient of phi, okay, dA, plus double integral over the area of the source dA. Okay. So first thing we notice is that for our convection term and our diffusion term, that the forms of this equation are perfect for applying the divergence theorem. Okay. So let's do that first. So let's simplify these integrals by using divergence theorem. Okay. And so remember, by applying divergence theorem, essentially we eliminate the divergence, so that we lower the order of the derivative by one, and we essentially replace that with the dot product. Okay. Okay. So then this becomes line integral around the boundary of phi multiplied by the dot product of the velocity and the normal vector, okay, is equal to line integral of the dot product of the gradient of phi dot product with the normal vector ds. Okay. And for the source term, we can't really do anything for the source term. So the source term, we're just going to leave it alone. Okay. Because the source term does not have any derivatives. And so that essentially is our conservation equation in finite volume form after we apply the divergence theorem. Okay. So this first term here, right? So the origins of this term here were from convection, right? So one way that we can kind of interpret this term is that this is the what we call the convective flux across the boundary of our finite volume cell. And we'll kind of remind ourselves what flux means in a second, but hopefully everyone remembers what flux is from Reynolds transport. Okay. The second term here, this is our diffusive flux. All right. And so basically what this equation is saying is that, if you look at our two boundary integral terms here, basically this is saying there has to be a balance between how much of the solution phi is transported across the boundary via convection, and that has to be balanced with the amount of phi that crosses the boundary via diffusion. Okay. So let's kind of remind ourselves what flux means, right? So flux is essentially just the transport of a certain quantity across a boundary. And so what those two terms basically means that, there's essentially two ways for our solution phi to cross the boundary. So it can cross the boundary of our cell either via convection or it can cross our boundary via diffusion. And remember, we've already kind of talked about the physical differences between convection and diffusion, right? Remember, convection is active transport. Convection means that, your whatever species that you have or whatever solution that you have is kind of riding along with the fluid velocity, right? Whereas diffusion is a more passive spreading. So diffusion happens, whether you have a fluid velocity or not, just because, things that are concentrated tend to kind of spread out evenly in all directions. Whereas convection is forced transport with. Okay? So no matter, which way that your solution is being transported, there has to be a balance between convection and diffusion and our source. All right. Any questions on this so far? Okay, so what we'll be doing over the next couple weeks is that, we'll be actually, going through the mathematical form for these, for these terms here. So we'll start with diffusion, just like we did in finite differences, and we'll see how that kind of mathematically kind of translates. The last thing I wanted to talk about today is the thing that's always forgotten, which is our source term. Okay. So for our source term, we obviously couldn't apply our divergence theorem there because there's no derivatives involved in the source term. There typically isn't. Okay. But we still need a way to evaluate that integral as well. Okay. We also are going to need a way to evaluate each of the line integrals as well. Okay. Right. And so this is where, up until this point, we actually haven't applied any approximations yet. So we haven't applied any kind of, computational tool. All this we've gone over so far. This is just kind of pure math. But in order to kind of get from a pure math problem to a computational problem, there has to be some discretization that has to take place. There has to be some kind of approximation, right? And so, the way that happens in finite volumes is through the evaluation of these integrals. Okay? And so we're going to introduce a numerical integration technique. This is probably the simplest one out there, called the trapezoidal rule. So kind of the funny thing about finite volume is that, even though we are working with these integrals, we're not actually going to perform any integrals, as ironic as that sounds, because, actually performing an antiderivative on an integram that, you may or may not know what the form is, that's obviously very difficult to do. And so the way we kind of get around that is we utilize these numerical techniques for computing these integrals, one of which being the trapezoidal rule. So essentially, the trapezoidal rule gives us a way to evaluate or numerically evaluate the result of an integral without having to actually perform any integration or any antiderivatives. Okay. Right, it's a very useful tool, you know, and you know, in a lot of ways, you know, if you once you kind of learn numerical integration, you'll find that in a lot of cases it's actually easier than performing integration than normal. Okay, but I do want to emphasize that trapezoidal rule, it's not a perfect method. So you know what you get from this essentially is just an approximation. So it's not going to be exact, and so you know you're not going to get an exact solution a lot of times. Okay. It is exact in some situations, and we'll talk about that in a second. But for for most cases, you can assume that there's going to be some error or there's going to be some discrepancy associated with it. Okay, so just like we did with the divergence theorem, I'm gonna show you the trapezoidal rule in all three dimensions, so 1D, 2D, and 3D. But unlike divergence theorem, you know, the trapezoidal rule is actually easier to kind of visualize in the different dimensions. Okay. So let's start with the 1D first. Okay. Okay, so for a 1D integral, let's say we have integral from a to b of some function f dx. Okay. So let's say that we want to evaluate this integral, but we don't want to actually evaluate the antiderivative of f. Okay. Okay, so trapezoidal rule basically says that, you know, if you take your integrand here and you evaluate it at the midpoint between your two integration bounds, so you take f of xc, okay, where xc here is the midpoint between your two integration bounds. So that's b minus a divided by 2, okay? And then you multiply that by just the length of your domain. Okay. That right there will give you your integral. Okay. Right, so the benefits for this obviously is that, you know, we don't actually have to perform any integral. You just take your integrand, whatever your integrand is, okay? You take that integrand, you evaluate it at the midpoint, and then you just multiply it by the length of your integration bounds. So you just multiply those two things together, and then that will give you your integral. Right? Very simple. All right, so I'm going to do a quick example just to kind of show you that this works. This is one of the few things I can actually show you an example of today. Okay. Because when you first see trapezoidal rule, as well as, you know, all the other numerical integration techniques, you know, there is some skepticism associated with it. Although if you're familiar with the concept of a Riemann sum, this is essentially that, but just a lot simpler. All right, so let's take the integral from 6 to 10 of 4x plus 6 dx. Okay. And so we're going to evaluate this integral using the normal way and the trapezoidal rule way. And what you're going to see that they're both the same. Okay, so let's do the classic way first. So the classic way to evaluate this integral is to take the antiderivative of your integrand and then evaluate it at the integration bounds. Okay. So the antiderivative of this is 2x squared plus 6x. Okay, and we're going to evaluate it from x is equal to 6 to x is equal to 10. Okay. All right, so we evaluate that antiderivative. We get 2 times 10 squared plus 6 times 10 minus 2 at 6 multiplied by 6 squared plus 6 times 6, like that. Okay. Right, so you can pull out your calculator and punch in those numbers and evaluate it, but I've already done that for you. So we do all that, we get 152. Okay. Okay, so let's see if we get the exact same thing using trapezoidal method. Okay. Okay, so trapezoidal rule says that we don't have to evaluate any we don't have to evaluate any antiderivatives. We can just take the integrand exactly as it is. Okay. Okay. And we're going to evaluate that integrand at the midpoint between our two integration bounds. So if our integration bounds go from 6 to 10, then the midpoint between that is going to be 8. All right, so if we do that, we get 4 times 8 plus 6. Okay. So this right here, this is f at xc. Okay. And then we need to multiply this by the length of our domain. So we're going to multiply this by 10 minus 6. Okay. This right here is length of domain. Okay. All right, so we do that. I've also gone ahead and done the math for you. So what we have here, that 4 times 8 plus 6, that gives you 38. You multiply 38 by 4, that also gives you 152. Okay. Okay. So you can see here for this 1D case, we were able to evaluate that integral and actually get an exact solution, without actually having to perform integration, for that case. Okay. All right, any questions on this example here? Okay. Okay, so that's the nice thing about trapezoidal rule is that it does work perfectly in some situations. And the situation that it works perfectly in is that if your integrand is a linear function, then your trapezoidal rule will give you the exact solution. So trapezoidal rule will still work, right? So even if you have a quadratic function, a cubic function, sinusoid, exponential function, trapezoidal rule will still give you an answer. It just may not be exact or may not be as close, if your integrand is something different than a method function. Okay. There are higher order, integration rules out there. Trapezoidal rule just happens to be the most simple. But for our purposes, trapezoidal rule is sufficient for us. Okay. Okay, so let me just show you very quickly what the trapezoidal rule looks like in 2D and 3D. Okay, so in 2D, This is the one we're actually going to use, right? So if we have an integration of some function, it's a function of two variables since we are in 2D, okay? And so trapezoidal rule basically says that, in order, if we want to find the value of this integral, we just evaluate the integrand at the centroid of our domain. Okay. And then we're going to multiply that by the area of our domain. And so that area could take a few different forms. For our purposes, since we'll be working on square grids a lot of times, the area of the domain is probably going to be delta x multiplied by delta y. That's just the area of our cell. Okay. Okay, and then very quickly, let's do the 3D. The 3D looks extremely similar. Okay. So once again, we're going to evaluate our integrand at the centroid of our domain. The only difference is that now we have a z dimension as well. Okay. And we're going to multiply it by not the area, but the volume of our domain. Okay, so basically for any integration terms that we can't apply divergence theorem to, we are going to use trapezoidal rule. And even for the line integrals that come out of our divergence theorem, we need to evaluate those somehow. And so we are going to use divergence theorem for that, or excuse me, trapezoidal rule for that. Okay. Any questions on this so far? Okay. All right. So for the last couple minutes, I do want to make a couple comments on accuracy. Okay. Because at the end of the day, finite volume is still an approximation method, right? And so, it has all the same, limitations as our finite difference method, okay? So when we were talking about finite differences, we talked a lot about the order of accuracy of our finite difference scheme, right? So we talked about first order accurate, second order accurate. Those same notions still apply, right? So we can still kind of assess or rate the accuracy of finite volume by its order of accuracy. Okay. So in general, what we expect is that, as you make your finite volume cells smaller, as you, decrease the grid sizing, you are going to get a more accurate solution. And how you approach accuracy, that's how we determine order of accuracy, right? So remember, we talked about, first order accurate, right? So first order accurate basically says that, as your grid spacing gets smaller, then your accuracy improves by that same order. Versus second order accurate, we have our error term determined by delta x squared. Right? So in general, for finite volumes, we still seek second order accuracy. But the way that we determine accuracy is different in finite volume. So the main determinant for accuracy in finite volume, well, there's technically two. The second one will become more clear once we actually start doing it. But one of the main determinants is how accurate your integration scheme is. And it just so happens, right? The integration scheme that we just went over, trapezoidal rule. Okay. Trapezoidal rule is second order accurate. Okay. So even though trapezoidal rule, relatively speaking, is very simple. It's a 1 point, we call it a 1 point rule, where you evaluate your integral just by evaluating a single point. It still has the accuracy requirements that we desire. Okay. And that's another benefit of finite volumes, that when you evaluate integrals numerically, it's a lot more forgiving in terms of accuracy. So it's much easier to obtain second order accuracy in integrals versus second order accuracy of just derivatives just by themselves. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for. So thank you guys. I know I went over a little bit, so thank you guys for staying a minute extra. So when we come back on Wednesday, we'll be actually applying this to diffusion equations, and we'll see what that looks like. And then we'll start to solve some finite volume problems. So thank you guys for coming today. I hope you guys stay safe, stay dry out there. I think the rain's continuing tomorrow. And I'll see you guys on Wednesday.
I have a follow-up question. Sure. When you're determining the sign, is it when the transaction is on the right?
Yes. Yes.
So this is like the standard one.
Yes, exactly. So it has to be on the opposite side of the diffusion source.
The only reason to move it over is when you were actually separating.
Yeah.
So that would be both positive and good. I was confused because I did it once with everything negative. Messed up my scheme.
Yeah, you have to be careful. You have to make sure it's on the right side of the right side.
Got it. Okay, thank you.
Yeah.
But Thursday I'll be here for a bit. Next week when I'm used to it a bit, I'll be here tomorrow. I think you're fired. What's up? You're fired.